Okay, so welcome everybody. We're happy and proud to have with us today Segev Wasserkrug. He's from IBM's research lab in Haifa. His background is more operation research, optimization, but in the last years he became more interested in game theory, decision making, and he's cooperating with quite a few of us in different interesting projects. He also has some patents. If you see in his, if you look at his website, you can see that. So interesting things, and he's going to give us a little bit of an industry point of view on game theory. And Segev, the stage is yours. You can share screen.
Okay, thank you very much, Galit, and the rest of the organizers for having me. I'm very happy to be here, and it's a great pleasure. So as Galit said, so I have been able to join at least some of the previous seminars. As Galit said, this will be different than the ones I've seen. It's not going to be very formal, going to be very few equations actually. But as Galit said, my background, I'm from the IBM's Haifa research lab. IBM has one of the largest industry research organizations worldwide. And while we do put great stock in academic eminence and publication and so on, that's one of the things we're measured. Ultimately, our goal is to help our clients and help IBM make business impact. And so this has been my focus and my passion throughout my career in IBM. And what I want to talk about today is how we can, or challenges in using game theory to extend this capability. So let me start with some background. So throughout my career in IBM, I've been very passionate, very focused on helping IBM's clients make better decisions through using formal, scientifically grounded methods. Now, so there are many ways people make decisions. Some are based on rules of thumb, some are based on automated rule systems. There's machine learning, but in many cases, the most advanced technique that currently we can get people to use is mathematical optimization, or what we call prescriptive recommendations based on a single party optimization. So the customer has a business problem and wants to do what's the decision. What's the best decision that I can make given this problem? And so the way when we get to that point, when we understand that there's a place for optimization here, we go through this fairly elaborate and lengthy process where we take the customer's problem and reduce it to what appears here on this slide. I say, okay, you have a set of decisions. This is denoted by this big X here, and you want to find the best decision that belongs to this X. This also contains all the constraints that could be taken on the possible decision, and you want to take the best decision so as to optimize some objective function, right? Which here is denoted by F. And you also have often a set of inputs that actually can't control. So, for example, if you think of a supply chain problem, the demand is not something that you can control, or the time it will take your suppliers to deliver the goods from the time that you make the order is also something that typically you can't control. So throughout my work in IBM, we've quite often been very successful at taking business problems and ranging from a wide variety of domains, including things such as workforce management, how to do optimal shift scheduling or workload allocation, things such as water network management, how to optimize pressure in a water network, so as on the one hand to make sure that water is delivered to sufficient pressure to the houses, but on the other, minimize the energy required to provide the water, and also ensure, because the more pressure that are put in the pipes and network, the more leaks and bursts are going to happen. So you want to find the optimal trade-off between them. I've found myself during a customer project at 6 a.m. in the morning, going and looking at pressure gauges and various areas of a client system. Another interesting project is optimizing the treatment of wastewater, so as to, on the one hand, ensure that the wastewater is cleansed to a sufficient quality to meet regulation. On the other hand, again, to reduce the cost or to minimize maximize the gas production from the wastewater treatment. So again, we found myself walking through wastewater treatment plants in Milwaukee at minus 20 degrees, walking through the snow to understand what's going on, look at the treatment plants and so on. So very, very interesting experience. But by the way, I haven't said so upfront. I have quite a few slides here. I don't need to cover all of them. I'd be very happy if this session were to turn into a discussion. So any questions you may have, please feel free to ask them as we go along. So as I said, this is something that that we've done quite a few cases, a wide variety. When I've joined IBM, I've never imagined to where I would have applied my expertise into use cases. But there's also quite a few challenges associated with applying these in the real world. And I want to mention them because these will carry over when we talk about applying techniques from game theory. So the first challenge is this belief in this type of use of math. So, and this is a statement that we've heard from many people. So we come to a client or to a customer who's trying to solve a problem, trying to find a better way of doing something, of making a decision, and we show that client this this technique, ultimately explain going to be reducing it to the equation that I showed on the previous slide. And the typical reaction that we hear is, no way is there going to be some algorithm or some mathematical techniques that are going to do a better job than me with my 30 years of experience, right? And that's I'm happy to say that when clients allowed us to go through these techniques, we've always proven them wrong. But this still needs to get past, and we need to address this. We need to show something working very quickly. We need to give them anecdotal examples. What I mean is we need to show them the types of counterintuitive decisions that can be made by such a system, and also enable doing what-if analysis. The second challenge is, how do we model real-world problems? How do we actually take the complexities and intricacies of a real-world decision and model it in a way that captures at least the primary points? And I guess you all know the saying, all models are wrong, but some are useful. So there's more of an art here. How do we take, again, the real world problem and at least capture the relevant parts in the formulation? And we're addressing this through several things. Of course, our experience, learning new techniques for learning part of the model from data, but also a very important part of the process is that these are not systems that make decisions, at least not to start with. These are systems that recommend decisions. These are recommendation systems. So we always start with making a recommendation to the user, saying, okay, look at the output of the system and you decide, you're the one that ultimately decides whether to implement them or not. Okay. Continuing on the challenges, so of course there's the computational challenge. Models for real-world problems are typically non-convex, highly discontinuous, and so here again we need to address these through. So the theory is never sufficient. We need to use relaxations, heuristics, And this is a very important point. This is actually an advantage of the real world. We don't actually need to get to theoretically optimal proven solutions. We don't need to show to the user doesn't really care whether or not the recommendation is optimal. What we need to do, we need to get to a recommendation that's sufficiently better than anything the user can get to without these system in place. So this is a very important point. This is actually an advantage of the real world. And also there's challenges around testing. So typically, as the goal of these systems to produce recommendations that are very far away from or sufficiently different. I wouldn't say very far away, but sufficiently different what the user is currently doing. So how can the user get any intuition on what these recommendations will be doing? Will they be safe? If, for example, I talked about the example of optimizing a water network system. How would the user know how would the user know that if they follow the recommendation of the system, all the pipes suddenly wouldn't burst and water would come bursting out, or they wouldn't start getting calls from hundreds or thousands of dissatisfied customers telling them I'm opening my tap and no water is coming out. Actually, we had a very interesting experience here in the scenario I told you about, where we did the solution, created the system, the recommendation, the system came out with a recommendation. I had no idea whether it was good or not intuitively, because I didn't have any sufficient background in water network. And we showed it to the operator, and the operator said, yeah, these make sense to me. Let's implement them all at once. And I said, are you sure? Do you really want to do this? And he said, yeah, it's fine. And luckily, indeed, we implement all at once, and it was fine. So this was, sometimes the user does have an intuition, but other times this intuition doesn't exist. So again, we need to address this or give sufficient tools for the user to understand what the recommendations are, how good the recommendations are. And the final thing I want to cover, or the final challenge, is how do we measure success? And as I said, the success is measured typically by showing improvement over existing decision process. But how can we prove this? How can we show that indeed we're successful? So one technique is to say, okay, let's agree on a benchmark measure. We calculate. So for example, if I talk about the water network, one of the goals there was to reduce the number of leaks and bursts resulting from pressure management. So we looked at the previous year, and we counted the number of leaks and bursts that happened in the previous year, and then we put the user used the solution for a year, and we compared the reduction in the number of leaks and bursts. And of course, that's not efficient, because we need to understand, or we need to try to clean out any noise. Are there any other changes that happened during that period that maybe they were the ones that caused this change? And so this is also a very important point, that we need the user to sign off on this. Now, there are also other cases, of course. These are more rare. These are less frequent, where we can do A/B testing. So in a very different decision problem, this actually was one not using optimization, where we put a system in place for diagnosis. And so what we did A/B testing, where we gave, this was for industrial, actually this was for an industrial company, a company manufacturing electronic goods that wanted to diagnose some of the problems in one of their appliances. So what we did there is, to some of the technicians, we gave the system. To other technicians, they didn't have the system. Then we compared over a period of, they actually kept all the records, and they compared over a period of several months what, the difference between the two, and again, showed very good or very significant improvements for the technicians who did have the system. But this is typically less frequent, that we can have this kind of A/B testing. So that's the single party optimization. I haven't said yet anything about game theory, so I'm about to move on. Any questions so far or comments? Okay, so again, don't be shy. If there's any questions, don't just ask in the middle. So these are this is the single party setting, but what we've seen in IBM, is that more and more recently, there are many enterprise settings in which a decision involves multiple parties, where each party wants to maximize their individual value, and the decision impacts the value of the other parties. And let me give a couple of examples where and in the broad sense, they fall into several areas, business networks, such as supply chain, which is the area I've been collaborating with some of the people on this call over the past months. There's also cybersecurity. This is actually very clear how this is a game, or very similar to a zero-sum or adversarial game, where you have the attacker trying to attack the system, and you have the defender trying to prevent the system being attacked or hacked. A scenario that would appear here is cloud computing. There's a lot of game theoretical work in the context of cloud computing. For example, Amazon has a spot pricing offering. And also there's this new trend where traditional algorithms or traditional problems in artificial intelligence have been addressed by using game theory. One actually maybe very well-known example is AlphaGo, where the deep learning algorithm has beat the reigning world Go champion, and and so if you under the hood, there's a lot of game theoretical techniques that went in there. But so let me give some concrete examples of how such multi-party settings. So the first, let's talk about a very simple supply chain where we have a retailer wanting to minimize inventory costs. So a typical decision looking from a single party optimization that the user wants to decide on the optimal inventory quantities to order from the supplier. There are uncontrollable variables such as ordering costs, arrival predictions, and so on. These are things that can't be controlled. And so the user wants to solve this optimization problem and reduce the costs associated with ordering inventory, right? So this is a single party setting, but there are other parties involved. So what could happen, right, potentially, is the traditional approach is, okay, I can't control, the ordering costs. I can't control the arrival predictions, but I have some models. So I use some machine learning models that tells me when I make an order, this is how long it will take. I take this model, I plug it in, a traditional machine learning model. So it relies on the data in the future being taken from the same distribution as the data in the past. And I want to optimize my inventory quantity. Same for ordering costs. I have, the ordering costs are from the supplier, but I can't really control them, but I don't expect them typically to change. But what could happen is we could get into this undesired feedback loop where the retailer hires us or someone else. They go through this problem of optimization. They get the optimal inventory quantities. And now they reduce what they need to order from their supplier. So then the supplier can come and say, sorry, and then they expect to be very happy because we show them the model and we say, okay, now your cost will decrease from say $100,000 to $50,000 or something like that, or $100,000 to $80,000. But then what could happen, right, is that a variable which we thought was uncontrolled actually is controlled, but is controlled by someone else. So now the supplier says, okay, you're reducing the order quantities. So right, so I've agreed. Our agreement says that I provide you a carton of milk for this amount, but this was when you ordered much more milk from me. Now you're going to order less. So unfortunately, I'm going to have to increase your price, which will cause ultimately the cost to increase above what what was initially predicted by the model. So ultimately, probably this will still result in a total decrease, but still much less than expected, because of not accounting for the way that the supplier could react, right? Another example, again, this is in the context of cloud computing or serverless computing. So I don't know how familiar people on this call are with the serverless computing model. So I'm going to give a little bit of background. So the traditional cloud computing, or the simplest cloud computing, when you go to one of the cloud providers, Amazon, Microsoft, IBM, and you say, I want to have a dedicated machine, and I want to have this machine, I want to run my workload on this machine. That's all the traditional, this is the dedicated, but there's also a very, and then the costs are that you pay for that machine, whether you use it or not. Just for the fact that you've been allocated, you pay for the machine, you pay for the operating system, say a fixed cost per month. There's a different model which is becoming more and more common, which is serverless, which says I don't dedicate a machine. I want to write some function. I want to write some code. I'm going to put it on your machine, on the provider's machine. And whenever I call that code, whenever I run the code, only then am I going to pay for it. Now, of course, if I have enough code running that the machine is constantly being used by my code, it'll be much more expensive for me when running the code. But typically, that's not what happens. But so I only pay when the code is run. So this is a traditional model, and so the decisions that have to be made now, from looking from the point of view of the cloud provider, is the possible number of servers to allocate. That's one decision. So how many servers? So I have a predicted demand, and I want to decide on the possible number of servers to allocate. And also, this will, of course, be an input to how much I want to charge for the serverless function. And again, typically, this is, so how would this be carried out using a traditional one-sided or one-party optimization problem? I have some model of the demand. I use some queuing model or some simulation model. I calculate the number of servers given this queuing model, and then I calculate the pricing for how much it costs me to keep up these number of servers, and then I charge the prices based on that number of servers. Right? That's all the typical approach. But what could happen is that I have my actual demand that I use to predict. I make my decision. I do the pricing based on it. But then what happens, now the client sees the price that I charge for the serverless decision. And they may say, okay, I want to use less than what I predicted. So now the demand is going to drop. And then I already have these machines up. I've already allocated them. I've purchased them. I've dedicated them. For what do I do? Right? I'm stuck. And this will actually show, using simulation-based analysis, using actual prices, and for allocating machines for one of the cloud providers, and we actually looked at what we did. We looked at the way that clients may perceive the costs of a dedicated versus a serverless architecture. Now, what I mean by perceived cost, because typically when you do a dedicated, you don't just take how much you actually pay up front. You also have to take into account the fact that you need to have people to support the machine, to keep it up and running. You need to buy the operating system. You need to apply updates. You need to keep the machine, all your software installed and updated and everything. Whereas the serverless, all of this goes away. The total cost is rolled into a single number. So this perception is very important. But we assume that the client will always choose a lower cost option. And we show that if you do take the multi-party recommendations into account, then the cloud provider will never lose specifically never lose money on the allocation decision for the serverless. Whereas if the single party decision is made based on some assumptions on the load and that the load will stay constant, then typically, unless you go to 2 times perception regarding the total cost, money will actually be lost in this when making this decision. So this is so now the question is, how do we move from the single party decision making to a multi-party decision making? And so the simplest is to say, so what did we say? We say, so first we need to take into account, so let's now expand this very high-level equation that I showed before. And so, okay, let's now add the impact of other parties' decision, or we need to bake that into the objective, but typically it doesn't just go straight in, because we also have to incorporate how my decision will then impact the other party's decision. So now we have to have this function of not just adding these other parties' decisions, but also taking into account how the decisions we make will impact them. All right. So this is actually, again, quite informally what we need to model. So now what actually happened here, we've taken this P, which was uncontrollable, and broken into 2 parts, one of which is the actual uncontrollable, at least things that are out of the model, and then the things that are being made by other parties that do want to account for, and adding this function that allows taking my or our decision into account. So if we look at at the previous examples, we look at the supply chains. Now GX is the cost of the supplier as a function of the retailer order quantity, how the supply will change, and serverless GX will be the price dependent demand function for different types of serverless users. So this is again, intuitively, or this looks like a nice way to do it. However, if we look back and remember this long list of challenges that I showed you previously, right? So now, not only do all these challenges continue to exist, the computational issues, this complex mathematical modeling, the belief, the ability to test. But now we've added additional challenges, because now I need to create even more complex models. I need to understand, the user needs to know, or needs to at least be able to model this G, and we need to efficiently then calculate this more complex problem. So how do we go then about addressing these challenges? So we looked around, right, and we said, okay, we're talking about multi-party. We're talking about how to add or make better decisions. And there's a very well-known science for making or for analyzing multi-party situations, right? We're all on this call very familiar and working with this, which is game theory. So is this the solution? Can we use game theory to then enhance these existing techniques to make these decisions in these multi-party settings? And it has a lot of very promising or very good concepts, right? So, for example, it has a model of the interaction between the multiple agents or players. It has a formal model of the impact on joint actions and individual player utilities. It has these accepted solution concepts, which we're all familiar with. And also it has extension to repeated settings. However, what happens is that there's another thing that happens, or additional challenges that happen when moving from a single party to a multi-party setting. So when I'm looking from a perspective of a single party, then I have full knowledge about the setting and convey that model. I'm only modeling the way I'm making decisions, right? I'm not modeling anyone else. But when I need to create a model about someone else, I don't have all the information often about how that person's environment or that party's environment, how that party is making decisions, how to take into account. The second is that when I make decisions, I can control my actions. I don't have control over the actions that the other parties take. So, and this is where the issues come when using game theory or trying to use game theory for prescription. So starting from very basic questions like, is Nash equilibrium even the right solution concepts for making prescriptive recommendations? Look at the assumption. It assumes perfect information. It assumes rationality, that everyone simultaneously tries to find the best response. And it assumes unbounded computational complexity. Remember, I can't even calculate often the optimal action in a single party. How do I do? And we all know that computing Nash equilibrium is not computationally tractable, at least as far as we know, in the worst case. So what happens when we move to this multi-party? Of course, there's no way to calculate this sufficiently. So many examples. There are many problematic counterintuitive examples like prisoner's dilemmas. We wouldn't want these to happen in the real world, even though it goes even beyond Nash equilibria to dominant strategies and so on. And even if we do find problems where we have perfect information, we can assume everyone's rational and it's not a problem to calculate it. It could also be multiple equilibria. So it could be that I'm aiming at one equilibrium and the other parties are aiming at other equilibria. And of course, there's the issue of repeated settings. So maybe the answer is going to other game theoretical extensions. Could we go to for example, maybe extended form games that give backward induction and have subgame perfect equilibria and maybe clear algorithms on how to make decisions. Maybe areas such as stochastic games, maybe looking at correlated equilibria, which is easier to compute, so or at least more computationally tractable, where we have an action drawn from a joint distribution, right? But even these have their own issues. For example, there's this centipede example, right? Which is problematic and counterintuitive. We don't want, and we also see this is not what people do in practice, and it seems wrong to tell people, if I'm making prescriptive decisions, it just seems somehow wrong to tell Anne, yes, in the first in the first round should also always go down and get 10 when you can go get much higher later on, right? And also again requires common knowledge of rationality, again going to this notion of common knowledge, and so on, right? Stochastic games, again, are computationally intractable in many cases. And correlated equilibria, there's always the issue of when and how can trustworthy coordination mechanism be implemented. Where do we get this magical coordination instrument? So the typical example is traffic lights, right? And this is, but how many other scenarios can we get such a very clear traffic light coordination between the scenario? Another issue again is that we need to know G. So if we look at, we need to know, or we need to be able to model G, this model of how our model or how our decisions impact other decisions. So let's look at the types of information in games. So we have full information for normal extended form games. We have common knowledge priors on type of players, which is assumed in Bayesian games. We have maybe even a less restricted, which is common knowledge of rationality. but there are many cases in this real world in which the knowledge or information is much more complex. So consider a two-sided market with multiple sellers and buyers, right? And need to negotiate on agreements between them, right? So if we want to use a Bayesian game, want to have a common prior, but why should S1 and S2 even share or have the same prior about S3's costs, which is important for making these decisions? Where do these common priors come from? There could even be even more complex situations that in some games, maybe some of the players are not even known. So S1 may not even know that S2 and S3 are potential sellers to the same buyers. So S1 probably know there are other sellers, but they not know who they are, not know how many they are, and so on. So this is another issue. So the type of information or how to model G, or how to get the information from modeling the G is another issue here. So what we've also looked at, or are still looking at, is can we use other related or different disciplines to making such decisions, and possibly tie it in to game theory. So first, of course, algorithmic game theory, which does talk more about computational tractability and so on. So it doesn't solve any of the others, but at least it addresses computational tractability and also does try to find simpler, in some cases, simpler mechanisms which are easier for people to follow. The other is looking at areas where learning comes into play. So looking at regret algorithms, both from the area of regret minimization and also from multi-agent reinforcement learning. But the issue about, for example, multi-agent reinforcement learning is that much less is known about the theoretical properties of these algorithms. In many cases, they're not even guaranteed to converge. The convergence properties are much weaker than the single agent reinforcement learning case. And as I said, we would like to have a more scientifically or a stronger theoretical basis to what we're proposing to our clients. So these are the additional areas that we're looking at, and so this is so these are, before I move on, these are sort of the primary issues and the big focus of our work, or the big focus of the challenges that we want to address. I have a couple of more. Again, I want to pause and see if there are any questions or comments so far. If not, I'll move on.
Yeah, just to clarify, for multi-agent reinforcement learning, you would say that the big problem is the lack of theoretical treatment for the algorithms to do that?
Yes, exactly. So I want to so the theoretical treatment, it's not just about the fact that we get good empirical results, but just don't have the theoretical basis to apply them. The fact is that we don't even know, we can't guarantee anything because we don't have the theory. In many cases, we can't guarantee anything about the empirical results that we'll get. Okay. For example, if we don't know whether they'll converge, we don't know whether we'll just keep the feedback loop that I showed before, right? Yeah. That we don't know if we use that will just keep happening. We'll just be chasing our own tail, just using a different algorithm, right? Yeah. For example, we don't know what it will converge to or how good it will be. Definitely not as compared to the traditional to the single party. And actually, there's also, I didn't write it here, but actually a lot of, for example, a lot of the drawbacks that I mentioned about assumptions of modeling others, this also is also required there. because it also requires making assumptions. So, for example, there's this competition on negotiating agents, right? But the way you negotiate also depends on what your party is trying to do. So there has to be some assumptions or some model of the other. So again, what's the appropriate models to use there? So, so it's not that just that we get good empirical results, we just can't justify them. It's that we don't have the theoretical basis to even get to create the initial learning from which we can get the good empirical results in many cases.
Yeah, thank you.
So an additional challenge is, for example, the value of information. Right? And this is a very interesting or subtle distinction that may or may not have been clear from my previous example. So again, if we go back to the supply chain, so one of the things that we've seen, actually one of the things that began us looking at this path of multi-party decision making, several years ago we saw this trend of many companies coming together using a common information infrastructure, a common technology infrastructure to share data, share information, so that they can together make better decisions. So if we go back to the supply chain example one of the first examples that I began with, so say that the way or the reason that the retailer can make better inventory decisions is because the supplier connected the GPS from their tracking system to their to the retailer, and now the retailer can have a much better prediction model regarding the time it will take for the new stock to arrive. So what could happen is that if the supplier does that, and then the retailer uses that information to reduce the inventory orders, the supplier could decide, okay, I'm going to disconnect my system. I'm not going to provide the information to you anymore. So what's the value or what's the value of providing that information? So that's another, so more subtle. The third is, sorry, not third, but another one is, how do we explain so say we come up with so that there are scenarios where we come up with these great algorithms and we can tell people how to behave. So and one very nice example is spot pricing for cloud resources. So spot pricing, this is something that Amazon enables on their cloud. And and so what you can do for workloads, so say machine learning workloads, which require a lot of resources and typically are very expensive to run, Amazon comes up and says, okay, what you can do, I have these many machines that you don't really care when the machine learning workload runs during the day. It doesn't have to be in peak hours. It can be at any time. I have hours in which my machines are not being utilized. I have hours where I have spare capacity on my machine. I'm going to offer these prices. I'm going to offer these machines to you, right? You can pay much less, but what I'm going to do, because I want to maximize money, I'm going to run an auction. So I'm going to, so you're going to offer to bid for machines at a particular hour, and if you win, you get those machines to run at much cheaper than if you do if you have to pay upfront for that. If you lose, of course, you don't get anything. Not only that, it could be, because these change every time, it could be that you run your workload, and if a higher bid comes in while in the next hour, or while your workload is still running, I'm going to stop your workload, take it off the machine, and continue it later when the workload becomes lighter. And so this is an auction. This is a very there's lots of theory, or lots of auction theory. This is actually one of the big successes, I think, of algorithmic game theory and mechanism design, how to run good auctions. So there's very strong theory here. Also, there are very simple auctions. So highest, ascending auctions, second price auctions, and so on. But now the user needs to, in order to use them, the user needs to understand, okay, how much do I bid? When should I bid? What would be a typical bid? Because this is more like a sealed bid auction, what I mentioned here, right? Everyone submits the price. I don't know what to bid. And I do need the resources. I do need to run my workload. I can't rely on, I need to know how long the workload is going to be running. So this is taken, these are taken from the Amazon, from AWS website. There's a lot of effort goes into clarifying to the users how much they should be bidding and simplifying the bidding process and clarifying what the chance that they get the resources. And also, by the way, there's a lot of work going into, okay, how do I, when I need to interrupt a user's workload, how do I stop that workload, but in a way that can be resumed later on. So I need to maintain all the computation, maintain all the histories that that workload can continue, not that it starts from scratch next time it is run. Otherwise, there's no use in it. So there's a lot of additional aspects that need to be taken into account when doing this, when applying game theory in practice, even when the theory and is there. So this is the big picture. I want what I can talk about next are some of the research directions that specific research directions that I've been working with many of them with people on this call. So the first direction, okay, so can we design mechanisms in which the best action is clear? For example, if we create VCG mechanisms for training networks in which the dominant strategy is incentive compatible, then it's clear how the users should behave, right? And then it's clear to tell the users, if you are participating in such a mechanism, this is what you should do. So this is one direction. Of course, we run very quickly into the Marsh and Satterthwaite impossibility theorem. So the question is, what do we do in those cases? Also, I mentioned that there's been a trend using a common infrastructure for sharing information. This is actually based on technology, on a blockchain technology, which may be familiar to some of you. So one way to maybe help with this is maybe implement a mechanism based on blockchain that will enable provide a trustworthy source for computing correlated equilibria. That's so this is in this case of how can we create such prescriptive mechanisms where the behavior is clear. Another direction, again, this is joint work with Galit, Janos Miklos, and Nimrod Megiddo. So specific knowledge information of real world settings. What happens when different players have different models of this G function that I mentioned, right? Of how players will act or will react to other players will react to my decisions. Are there some beliefs, are there some models of G that are better than others? Are there any conditions under which a single party is better than a multi-party? Maybe there are cases where we should go back and tell people, you shouldn't actually take, if you try to take other people's reaction into account, you do it in the wrong way. Maybe this will actually lead to poorer decisions than if you don't. In repeated, if we use learning, how much exploration should be used, how worthwhile would be to mislead opponents by taking a suboptimal action so they learn the wrong things. And the fact that the ability to learn, can they actually change the equilibria? So these type of questions we're looking at. Moving directly from that, moving to learning. I mentioned regret minimizations with Nicolo, Marco, Tom, and Osogami-san, also from IBM, looking at, so regret minimization, how can we use that to make better decisions, looking specifically at supply chain games and multi-agent reinforcement learning in supply chain games, similar work. And also there are other effects that can impact or that can happen in real world situations. For example, players can decide to leave the game. So this is an example of a trading network where we have two suppliers and two retailers. And there is, this is work with Miklos and Aylon. And here we have what we can see is that the traditional solution concepts, such as competitive equilibrium in trading networks, if they don't take into account the fact that players who can analyze and understand they're never going to leave the game, they'll come with solutions that actually give zero or can give zero utility to some players. But just the presence of these players is beneficial to other players who do get something from the game. So if we look at this example of two retailers and two suppliers, so if one of the suppliers, so say a supplier, there are two suppliers who are equivalent and can provide the exact same goods, but one supplier has a higher production cost. So obviously, everyone will want to purchase from the cheaper supplier. So the more expensive supplier doesn't get anything. But then if that supplier leaves the game, then that single supplier that remains becomes a monopoly, and they can charge a very high price for their good, much higher than what would have been paid to the more expensive supplier. And many of the traditional solution concepts actually say you should give zero to the remaining supplier. So again, this seems problematic, and this is another area where we're looking. So to summarize the vision, right, or the goal, and we know, and I said initially that our ultimate goal is in IBM research, is to help our clients and IBM make better business decisions and make more business impact. But we know that in many cases it requires driving forward the science. So we see this more as a scientific endeavor, this project, a longer-term scientific endeavor, not something that we intend to solve immediately, of course. So this is our vision, to combine an advanced game theory, algorithmic game theory, and learning to provide a scientifically sound prescriptive algorithm for multi-party decision making. This is our vision. Of course, we would like to show concrete proof points and success proof points along the way, but currently our focus is on driving forward the science around this. Now, throughout the talk, I've given, I've talked about the need. I've talked a lot about the challenges and the difficulties. So why should we succeed? I mean, you should say, okay, do we even have a chance of doing something here, right? And so I do want to, and actually I think we do have a good chance, and I want to start with what do we mean by success, right? Or what would be success from the business case, and going back to how I define success in the single party setting. What we want to, remember how we defined success in the single party setting, we said we want to do better than a single party decision process. So what I want to do, or success for us in this endeavor, would be, can we show improvement when taking other parties' decisions and actions and models into account? Can we show that we'll be doing a better job than if we don't do that, right? So it's of putting the bar perhaps a little lower or significantly lower than pure science, but this is still a fairly difficult bar to meet, right? But at least it may give us more hope in meeting it. The other is that even just considering the other party's objectives and possible ways of action can already provide valuable insights. Even thinking about the fact, okay, do I want to take this into account? Don't I want to take this into account? What to take into account I can compare, or it gives tools to compare between, okay, what would happen? What are the decisions I would make if I don't and take those into account? The decisions I make if I do take this into account. The ability to learn over similar and repeated interactions. So again, so I have a wrong model. Okay, that's fine, but at least maybe I can learn, and maybe if I learn, at least at some point I will come to the right model, and then I can converge. And another important, a very important point is that real-world settings often gives you the ability to change the game. So you know where your blind spots are, you know what you need to learn. You don't have to consider it adversarial. Just reach maybe the ways to communicate with the other party and pass on some of the information, or get some of the information that is missing. Maybe you have a way to define the game or influence the game. The mechanism design is clearer, right? If, for example, the information that I provide, the information that I don't provide, and how I implement the implementation of, for example, spot pricing on the cloud, that could have an impact, and so on. So these are all aspects of the real world that we can use, right? And so think outside the box. Since what can we add? What can we do in this real world settings, in addition to the tools that that game theory and the other disciplines give us to come up with these methods and techniques. So to summarize, our goal is to obtain a scientifically sound method for providing prescriptive recommendation multiple decision-making. I've provided some real-world examples and gone through the issues in great details. And as I said, we want to achieve this both by driving forward the science and working with you, but also when applying it to utilize the advantages of the real-world settings to, as much as possible, mitigate the gaps, or the scientific gaps that will always continue to exist and need to be addressed. So that's it. And I think we have a couple of more minutes for questions or discussions.
Thank you, Segev. Thank you. And if anybody has questions, now is a good time to unmute yourself and ask them. Well, maybe I begin. It's not really a question. It's more of adding to your optimistic ending of the talk. Another advantage that maybe applying our solution concepts to real life might have theoretical solution concept is that in theory, when we have a solution concept that works very well on some games, but doesn't work on other games, or it doesn't make sense in other games, we tend to be very disappointed. Why we want to have a solution concept that solves the universe altogether, while in real life, it's often the case that you're not expected to solve the universe or all games. You need something that applies to a specific problem that you have at hand. And if you can do well, you can do good, you can do better for this problem, then maybe it's better than doing nothing. So maybe this is another thing, that you don't need to solve everything or to get very disappointed if what you did for auction does not work when it comes to optimizing something else.
Yes, actually, I think that's a very important point, and that's actually another point that's important for me to make. So I want to be, it's not that, it's always about alternatives, right? In the real world. What I mean is that people typically they didn't sit on their hands and do nothing and wait for IBM to come and model their problem and say this is what should be doing. They are doing something right now. They're making decisions in some way, based on some information, based on in an uncertain environment, based on rules of thumb or others. The more tools we can give those people to make better. The more tools, diverse tools we can give those people who are making decisions, right? We can expect them to make better decisions using those tools, right? Better than what they've been doing. So it's not about, as you said, but it's not about solving the universe. It's just about providing additional alternatives and being very clear and giving the tools to people to understand when those alternatives are indeed better.
Yes, this is a little bit also in the spirit of the talk that Olivier Gosner gave here and also in the workshop, that maybe sometimes we don't have a solution concept that works perfectly for everything, but give me a game and maybe I can apply something that that refers to the specific attributes of the specific game. Yeah. People, more questions or remarks, please just feel free to unmute and add to the discussion. Okay, so in this case, we're going to thank you again for coming.
Thank you very much for having
talking
me.
to us, and I will stop the recording.